Thanks a lot, Joe. Thanks for the kind introduction. Once again, it is very nice to see many of you once again on this virtual floor. So this talk will be a little bit different and new in the sense many of you are familiar with our MPI project, the MVAPICH project Joe introduced. We have also done in the past separate project on big data, like the high performance big data stack, where we did RDM-based designs for Hadoop, Spark, HBase, Memcached, Kafka, a lot of those. But now we are heading into a new direction where we can actually run all these big data stacks over MPI. So that is actually the new contributions here, and we'll go into more details and show why we want to do that, and if we do so, what will be the benefits. Okay, so Aamir, next slide, please. So the outline will be as follows. We'll start with a very high-level introduction to the big data analytics and also to the MVAPICH2 project, if some of you are not familiar with. And then we'll go into two especially software stacks we'll be focusing. One is on the Spark and the another is on the Dask. And for each one, we'll try to show how you can actually link it to the MPI library. So we have MPI4Spark and MPI4Dask. We'll provide an overview, design, and implementation, and also try to show performance evaluation for these two stacks and the related publications and summary. And you will see that not only we have published here, we'll show you some results. These are also available for download. We'll give you the pointers if you would really want to run Spark over MPIs, Dask over MPI. You should be able to download and run these and get great performance and scalability for your applications. Next slide, please. So at a high level, as you know, the big data analytics, I mean, it has been there almost like for last 15 years or so. It has changed the way people understand and harness the power of data, both in the business world as well as the research domains. And especially in the enterprise domains, data centers and all, big data has become one of the important elements to carry out the business analytics. And this is where we see the convergence, what is happening between HPC and also the big data field, especially when you have large data, not just the size, but we also have the need to have the computational power. So you bring them together to solve your analytics problems. So in this talk, we'll focus on two of these frameworks, the Dask and the Spark. And especially Dask these days also is being renamed like a data science. I mean, this big data analytics and data science, they're like a almost like a converging with a very similar objectives kind of things. Okay, next slide, please. So this is where I just want to give a short overview of the MVAPICH project. If you are not familiar with, we started this project almost day one of InfiniBand. If some of you remember, like InfiniBand was introduced in October 2000, almost 22 and a half years back. So when prior to InfiniBand, those of the old timers must be remembering, we had a lot of clusters running with Myrinet, Quadrix. Those were the networks, state-of-the-art networks at that time. So when InfiniBand came, we were the very first one from our group to jump in and try to explore how you can actually build a cluster with InfiniBand and run MPI, which is the message passing interface standard, on top of that. And then the question was, will it give good performance, scalability compared to the prior networks like Myrinet and Quadrix, which were proprietary networks, and InfiniBand was an open standard. So we were there. We started immediately working as soon as the InfiniBand was publicly available, and we had a first demonstration at Supercomputing 2002, almost again 20 years back. I still remember it was in Baltimore, and people were very surprised and very interested to see that an InfiniBand cluster is actually running MPI. But of course, at that time, it was very hard even to keep an 8-node cluster running on the demo floor. It was a challenging task. But now, of course, in 20 years, a lot of things have changed. And now you see thousands of nodes are being deployed with InfiniBand and the variants like Rocky and all. So I'm very proud of my team. We are continuing this project. It is 22 years and counting. And even though we started with InfiniBand, as you see, we have extended it to all different interconnects now. Omni-Path, Ethernet iWork, Rocky, even AWS Elastic Fabric Adapter, Omni-Path Express, Broadcom Rocky, Intel Ethernet, Rockport Networks, Slingshot 10 and 11. So you name any of the high performance networks these days, which are very commonly used, and we have the solution for that. And it is not only the network side. We have also focused on the platform side. We support all like a x86, OpenPower, ARM, the older Xeon also we supported, and these days also GPUs, all NVIDIA and AMD, and the support for Intel GPU is coming, and you will see very soon also support for FPGAs. So those are in our pipeline. And as Joe indicated, currently is being used by more than 3,300 organizations in 90 countries. These are the voluntary organizations. And we have crossed just from our website 1.66 million downloads just from the OSU website. But of course, MVAPICH library is also available together with a lot of vendor stacks and a lot of distros like Red Hat, SUSE, OpenHPC, and also it is has been integrated with the Spark manager for the last several years. So, and not just the count, but it's also empowering a lot of top 500 systems. You will see MVAPICH being used as a production library on many of these systems. So we want to leverage this kind of environment, not only just for the HPC side, but also for the big data and machine learning, deep learning, so that you can actually design a converged framework. And especially if there is a workflow which involves multiple of these stages, like sometimes you do, let's say, HPC followed by data analytics, followed by AI, you don't need multiple of these stacks. You can actually use a one stack, and that's what is our goal here, and we are heading into that direction. Next slide, please. So this is the overall architecture, how we have been doing. In the very beginning, we started with only MPI, but over the years, we have started, if you see at the top level, not only MPI, we have PGAS, hybrid MPI, plus X support. So those are at the lower levels, at the API levels. And then below, if you see the lower bottom corner, you will see these are all the different networking technologies. And as I indicated, since last year, we actually support also OFI and UCX, those of you are familiar with those. So that means even if some network is let's say at a very lowest level, like a VERS that is not available, and if that network is exposed through Wi-Fi or UCX, MVAPICH will run on top of that. So that is our new 3.0 series. If you have not used that, please feel free to use. And the right-hand side is also like trying to take care of all the different architectures, including also the DPU, the very latest NVIDIA's Bluefield 2 and Bluefield 3. And then, of course, the middle part is the scalable communication runtime. This is what we've been working on many years. And you will see here how we have linked, especially the Spark and Dask with MPI there. And with this architecture, now on the top of it, today in this talk, we'll not be focusing, but we have a project called HIDL, High Performance Deep Learning. So we have actually through Horobo, DeepSpeed, those are the kind of the modules we have actually linked to the MPI, so that you can actually through MPI, you can run all these stacks. You don't need any other the collective communication library like Nickel, Rickle, Sickle. And in fact, we deliver equal or better performance compared to all those libraries. So if some of you are interested, please feel free to take a look at the HIDL, High Performance Deep Learning site. We'll not talk about that today, but we'll be talking about the high performance big data. Okay, next slide, please. So this is where we'll start with the MPI4Spark. Next one. So if you take a look at like the Spark, like we had done a lot of work on RDMA Spark. So that means the Spark layer, the Apache Spark, if you remember, it just runs on top of TCP/IP. So what we did is actually, this was almost like 10 years back, we took it directly to the InfiniBand and to the Rocky. Okay, so using the VERS level API, so we redesigned the lower level, and it delivers very good performance. You can still download and run it. But then what is happening is here this new motivation comes as newer networks are coming. Let's say Omni-Path is there, Slingshot 10, Slingshot 11. The same design can still be used, but it will require a lot of effort. Okay, I mean, at that time we did it almost, it took us like 2 years to bring the complete Spark design to the InfiniBand VERS. Now the question is it beneficial for us to spend every 2 years on newer technologies? But the alternative is that as these network technologies are evolving, MPI is very widely used on any newer clusters come up. MPI is the first library to be used there. So then the question is, why can't we leverage? Because MPI almost these days, not only our MVAPICH2, many other MPI libraries deliver very close to the bare metal performance with a little bit performance loss. So why don't we reuse that MPI library? So we are trying to change the levels. Instead of working at the first level, we are taking it to one level up. So if the MPI library is designed properly, then we can actually bring all other the frameworks on top of it. And that's what you see here. This is like how we use the MVAPICH2 to optimize the Apache Spark. So if you take a look at the right-hand side figure, so here the right-hand side, you will see that we have the Spark core. Of course, inside that is the support manager. Then we have these block transfer services. And this is where there is a native transport. So that native transport has been there for the client side. So what we try to do is the native plus MPI transport. And that actually is linked to a MPI Java bindings. And we actually have an MVAPICH2J release, which is the Java binding release, which we did earlier last year. And then through that, we can actually go to the Java native interface JNI, and then you can actually, all the Spark communication calls can actually utilize the native MPI communication library. And what it means that now we can actually use any network which is being supported by the MPI library. So that is the whole idea of this new work, so that we can reutilize the MPI point-to-point communication inside NETI, and then that can get translated to the Spark layer. So next slide, please. So this is the overall idea here, putting it all together into one slide. More details are available, and the actual code is available from this HIBD, which is the HIBD site. And this is where I was telling you can actually download RDMA Spark, supporting only InfiniBand and Rocky. That has been there for many years. But then, of course, with every new interconnect, we have to redesign. So instead of like the right side, which is the older design of this table at the bottom of the screen, RDMA Spark running with the unified communication runtime with IB verbs, which was only allowing support for InfiniBand and Rocky. Now, if you see the left-hand side, so here we go through the MPI4Spark, which is running over MVAPICH2J with the Java binding with the MVAPICH2, and now we can actually support all interconnect. And in fact, you will see in the next few slides, the same stack can now run on, we have numbers on InfiniBand with Omni-Path. We are trying to take numbers on all different interconnects, and with very little overhead. This approach is a performance portable approach. And if we move forward with this, anytime a newer network technology comes up and there is an MPI library available for that, we should be able to immediately take advantage of that for the big data frameworks. So from here onwards, I'll hand over to Aamir. We'll go into more details of the design, the performance numbers, and the future plans and conclusion. Aamir?
Thank you, Dr. Pranam. You can hear me, right?
Yes.
Okay, so one of the first challenges that we had to deal with while implementing what we call MPI4Spark was that the Spark is basically forking off new processes. So typically, if you look at the execution model of Spark, there is a master process, there is a driver process, and then the cluster consists of workers as well. And these workers are responsible for executing user application. And it's possible that multiple applications might be running on workers or compute nodes at the same time. So for that reason, every time one of the client connects to execute their job, the worker is going to spawn and what is known as an executor process. And typically MPI, most of the MPI static applications which rely on MPI COM world don't cater for forking processes, especially if they have to communicate. So here is, this figure is basically showing, our approach, how we dealt with that. We basically exploited the MPI dynamic process management feature here. So for example, in this case, starting from the left-hand side, if we have, let's say, 4 processes, so these are basically started using MVAPICH2, and then, these processes assume the role of couple of workers, master and driver. And then, when it's time to execute the job, the worker processes are going to fork off a couple of new processes called executor A and executor B. If you look at the node view level of these things, then, the executor processes. So for example, in this on node A, if we have worker A running here, then we would want executor A to also be launched on this particular node. And another challenge here is that in the case of DPM, there are several new communicators available. So for example, if the existing processes, couple of workers, master and driver, if they need to communicate, they will rely on MPI COM world. But then, the newly launched processes are part of a new intercommunicator that we are calling in this figure DPM COM. So if executor A is talking to executor B, they will communicate using DPM. However, if the worker A, let's say, needs to talk to executor A, they will need to rely on an intercommunicator. And essentially, MPI defines, there are different semantics for communication between different processes in this case. So one of our earlier design was, so on the right hand side we have basically an overview of how the netty selector loop operates. So this is basically the key here is this select function. This is very similar to the select function in the C programming language, which lets you multiplex between multiple communication channels. So in this case, what's happening here is that multiple sockets in the form of socket channels, they register themselves with a particular selector, and you can think of this selector as a while true kind of a loop, except that it's not polling, and this is event generated. So these channels would register with the select message, and every time any of the registered channel has, let's say, an incoming data to read or a new connection, an event is generated, and then netty would basically go on and deal with that event. In our first design, what we did was we replaced this select call with MPI probe. So MPI probe is a non-blocking probe call, and if you have a process and you're expecting, let's say, new messages, so you could probe for incoming messages, and then depending on the source and depending on the tag, you would decide to call particular receive. You would decide how to exactly receive the message. So the downside of this particular design was that this was too CPU intensive, and for that reason, we ended up consuming a lot of CPU for the communication code in Spark. So later we then moved to an advanced design here. So the advanced design only focuses on the shuffle messages. So in the previous design, all the control messages, the heartbeat messages, they were converted to use MPI. But in the newer design, so this figure is basically showing you all the types of different messages communicated by Spark, but we only focused on the messages that are basically doing shuffle, so which is stream response and chunk fetch success. So we only focused on these couple of messages for implement these were basically the candidates where we wanted to use MPI. So in our optimized design, we only, as I said, target shuffle messages, which account for 80% of the total execution time, depending on your particular workload. And this way, we were able to avoid the non-blocking MPI probes. And the idea here was that we would leave the communication of Spark intact. Instead, we'll just every time we receive a message, we'll basically look at the header of incoming messages. So if large data is coming in, or if shuffle messages are being exchanged, we have that information in the header, and we'll basically use we'll utilize that information and subsequently call MPI based communication. So this was the overall strategy in the optimized design. So we have actually released this work, and MPI4Spark 0.1 is available for download, and this is from our HIBD website, and this is based on Apache Spark 3.3 version, and I mean it's compliant with the user level Apache Spark APIs and packages. So if you have an existing Spark application, it should be able to, you should be able to run that using MPI4Spark. And this makes use of the Java bindings that we wrote for MVAPICH 2. And then we have tested this work with a variety of applications and benchmarking, including HIBD, Intel HiBench, and this was also tested on a variety of network and platform, configurations. So with this now, I'll move to MPI4Dask, which is basically a similar thing, but for Dask. And Dask, as many of you would know, is a popular task-based distributed computing framework. This basically scales Python applications from laptop to high-end systems. So the same application that you write on your laptop would scale on high-end systems. And under the hoods, like Spark, this maintains a task graph, which is then executed lazily on the parallel hardware. So historically, Dask distributed, which is a layer inside Dask responsible for parallel and distributed execution, has maintained two communication backends. One is TCP and one is UCX. So the support for UCX was added a few years ago by the NVIDIA Rapids project. And what we have done here is, in the same sort of spirit that we have implemented MPI4Dask communication device, which provides an MPI-based backend for Dask, and this is done using MPI4Pi. So we didn't have to write a wrapper in this particular case because MPI4Pi, which is a very popular library, it's already available, works with the MVAPICH 2, and we relied on that. And again, so the ecosystem of Dask actually already supports at least launching Dask programs using MPI. And for that reason, this project called Dask MPI, it already exists. So if you would like to, let's say, launch execution of your Dask program without using what we have done, you could just use Dask MPI project and use that to launch your Dask applications. And a lot of the people running Dask on HPC systems, they already rely on this Dask MPI package. So here is the execution model of Dask. So in this particular case, we have a scheduler. Multiple workers would connect to it, and together, the scheduler and all the available workers, they would form what is called a Dask cluster. And then the client connects, submits the job to the scheduler then schedules them on the workers, gets the job done and brings the results back to the client. And the key characteristics here are scalability, so we would like to achieve, best possible performance, elasticity, the workers can come and go. So Dask internally is implemented as an async IO application. So, if you're adding new functions, if you're adding new functionality, they need to be added as coroutines. And then as part of the Dask NVIDIA Rapids project, support for GPU-based computation was also added to the Dask ecosystem. And here is the architecture diagram here. So starting from the top, we have the Dask layer, different data structures used to program your Dask applications. And then we have these different projects like Dask MPI, Dask CUDA, Dask JavaQ. So these are different packages and projects provided by the Dask ecosystem that let you execute things on HPC systems. And then this distributed is pretty critical. This package provides support for parallel distributed execution, provide notions like scheduler, worker, clients, and it also provides support for the communication layer. So as I mentioned earlier, TCP support was already there. UCX support was added by the NVIDIA Rapids project. And then as part of this work, what we have done is we have added support for what we call MPI4Dask. And essentially this is MPI support for communication in Dask. And in this case, the first challenge here was the bootstrapping and dynamic connectivity. And so we actually relied on the Dask MPI project to essentially, enable bootstrapping execution of Dask programs using MPI. So apart from, MPI connections of processes to one another, we also had to establish dynamic connectivity, using the async IO package in MPI4Dask. So we had to do this to essentially implement the communication interface provided by, the Dask API, which lets you write new communication backends. And then the second challenge was we had to implement this point-to-point communication coroutines. And what basically this communication coroutine means is that we had to wrap our communication functions in the form of coroutines. And in coroutines, it is not possible. I mean, if you would call, let's say, blocking send and receive functions, we would end up, blocking the whole, deadlocking the whole application. So if we just focus on the left-hand side here, which is basically our send communication coroutine, we implemented this using iSend, which is, non-blocking send in MPI, and this is then followed by test, right? So we initiated the send operation using iSend, and then we are testing that, has that communication completed or not. So if it is not completed, then, we sort of relinquish the CPU using this async io.sleep, because there might, for a particular thread, there might be other communication coroutines or compute coroutines that would like to, utilize the CPU. So we are basically, giving up the CPU to those other coroutines. And then once we are back, once, the communication of this coroutine is resumed, we call the test again, and we do this in a while loop essentially. And then we also implemented a chunking mechanism for large messages, because MPI typically HPC based applications, they don't deal with really large messages. And by really large messages, I mean, hundreds of megabytes up to gigabytes. So it's very common for Dask and, other big data frameworks and applications to communicate such large messages. And MPI typically, I mean, it's possible to execute up to a certain limit, but, we had to implement this chunking mechanism to achieve a better performance in MPI4Dask. Right, and then MPI4Dask work has also released as from our HIBD platform, and so I would invite all of you to basically go and kindly give it a try, and let us know if you have any feedback. So with this now, I'll move on to the evaluation of this work. So I'll start off with MPI4Spark, and here we are basically doing weak scaling evaluation using OSU HIBD benchmarks. And on the left-hand side, we have the group by test. On the right-hand side, we have the sort by test. And basically, we have a set of, let's say here, the first 3 bars here are on 8 workers using almost 500 CPU cores. And then the next 3 bars are on 16 workers, and the last 3 bars are on 32 workers. And for each, sort of combination of workers, we run vanilla Spark, which is, represented as IP over IB here. And then we have RDMA, which basically means this is our RDMA Spark software. And then MPI basically means that this is our MPI4Spark work. And as you can see, we are actually seeing really good performance compared to TCP and even RDMA Spark as well. So for example, for this particular test, we are seeing around 2.2x speed up compared to RDMA Spark, and almost 4x speed up compared to TCP. We also see similar gains for sort by test, and these tests were done on the TACC Frontera system. Similarly, we also did evaluation with Intel HiBench workloads. So these are higher level workloads, like ML workloads, graph workloads. The first 2 graphs here are on TACC Frontera. So we are using InfiniBand here. We are seeing speed ups compared to RDMA Spark around 1.4x. But then this last one, the right hand one, is on the TACC Stampede system, which is which has Omni-Path interconnect, and RDMA Spark obviously would not run here, but MPI4Spark solution would just run out of the box here. And we are also seeing good performance compared to vanilla Spark on this particular system. So moving on to the evaluation of MPI4Dask. So this is evaluation done using a benchmark called QDF merge benchmark, and this is done on the University of Cambridge in the UK, their Wilkes 3 system. Here are the details of the Wilkes 3 system. So on the left-hand side, we are plotting execution time, and on the right-hand side, we have the aggregated throughput. So I will just focus on the execution time, and we are basically, we are actually seeing very good performance compared to TCP, around 25 times better and around 5x better than UCX as well. So we don't only see the gains for GPU-based applications, so we have another benchmark for CPU-based Dask application called NumPy array slicing, and this is on the TACC Frontera system. And in this case, on the left-hand side, we have again the total execution time, and we are basically seeing, so the gains on the CPU-based systems are not as pronounced as on GPU-based systems, but we are seeing around 26% or 37% better performance than UCX and TCP. So with this, I will hand it over to Dr. Panda to conclude this talk.
Yeah, so next slide, please. Yeah, so as Aamir said, that we have several publications along these lines. We have the initial paper we presented at IEEE Cluster 22. We had the Java binding paper at the HIPS 22 workshop in connection with IPDPS last year, and also the Dask paper was published at the CC Grid 2021, and also the Java binding paper was in the HiPC 2020. So please feel free to take a look at these papers. Next slide, please. So to conclude here, as we showed in this talk, like Apache Spark and Dask are two popular big data processing framework. There is existing support for the parallel distributed on HPC systems, but as these frameworks really require very good high performance support for low latency and high bandwidth. And this is where we have done this work, trying to provide support for Dask and Spark over MPI so that we can actually have a performance portable designs, and then it can be used on any new interconnect whenever it is available and MPI library is available. We should be able to directly take advantage of it. So with this, let me conclude here. We'll have a few minutes to answer any questions people might have. The next slide actually shows our contact. If you have any questions, please feel free to post it on the chat now or send us an email, and we'll be very happy to answer that. Thank you.
Thank you, Dr. Panda and Dr. Shafi. Do we have any questions? We don't have any questions on chat. Does anyone have any questions before for these two doctors? Okay, well, thank you very much for your talk. I enjoyed it.
Thank you.
Thank you.